What specific problem does your proposed method aim to address in the context of enhancing reasoning abilities in LLMs?
The proposed method aims to address the challenge of enhancing the reasoning abilities of large language models, LLMs, without relying on human annotations or stronger LLMs. Specifically, it focuses on improving the reasoning process through self-training, where LLMs generate their own training data by exploring step-by-step reasoning paths using Monte Carlo Tree Search, MCTS. This approach allows for the iterative generation of training data that captures partial solutions and their subsequent steps, which are then used for supervised fine-tuning. By leveraging process supervision instead of outcome supervision, the method seeks to instill a more robust reasoning capability in LLMs, ultimately leading to better performance on reasoning tasks. The effectiveness of this method is demonstrated through significant improvements in accuracy on mathematical reasoning datasets, indicating its success in enhancing ILM's reasoning abilities.
How does the proposed method work? Please illustrate the process step by step, including details on how MCTS is integrated and the flow of data.
The proposed method enhances the reasoning ability of LLMs through a self-training process that leverages Monte Carlo Tree Search, MCTS, for data generation. Initially, a dataset of reasoning problems and their answers is established. For each problem, the method generates a training dataset by treating each step in the problem-solving process as a tree node, where MCTS is employed to explore potential next steps. The process involves 4 key steps: selection, choosing the child node with the highest upper confidence bound; expansion, sampling the next step as a new child node; simulation, continuing the partial solution until a final answer is produced; and backpropagation, comparing the final answer with the ground truth to update node scores. This iterative process continues until a new partial solution is formed, which is then used for supervised fine-tuning of the LLM, repeating the cycle until convergence is achieved.
Can you provide a simple example demonstrating the inner workings of your training algorithm using a reasoning problem and how MCTS is applied to it?
Certainly. Let's consider a simple reasoning problem, such as solving the equation what is 2 plus 3. In our training algorithm, we start with the partial solution 2 plus 3, and apply Monte Carlo Tree Search, MCTS, to explore possible next steps. Initially, we select this partial solution as the root node, and use the LLM to generate potential next steps, such as 5 or 4. During the MCTS process, we would simulate these steps by generating continuations until a final answer is produced. For instance, if the LLM generates 5 as a final answer, we compare it to the ground truth, which is also 5. We then backpropagate the reward, 1, 0 for correct, through the tree, updating the visit counts and cumulative rewards for the nodes leading to this answer. This iterative process continues, allowing us to build a dataset of reasoning paths that are then used for supervised fine-tuning of the LLM, enhancing its reasoning ability over time.
What are the key theoretical and practical advantages of your approach over existing methods like zero-shot COT and rejective sampling fine-tuning?
The key theoretical advantage of our approach lies in the use of process supervision for training LLMs, which avoids the complexities and instabilities associated with reinforcement learning and reward models. Practically, our method demonstrates superior performance in generating training data through Monte Carlo Tree Search, MCTS, allowing for the exploration of optimal reasoning paths, which is more effective than the selection of best and worst steps used in rejective sampling fine-tuning. Experimental results show that our iterative training method consistently outperforms baselines like zero-shot COT and rejective sampling fine-tuning by significant margins, particularly in accuracy improvements during training. Additionally, our approach exhibits better transferability across different datasets, confirming that the LLMs enhance their mathematical reasoning abilities more effectively than existing methods. Overall, our method not only improves reasoning capabilities, but also ensures a more stable and efficient training process.
How did you validate and test your proposed method? Please describe the datasets used and the metrics applied to evaluate performance improvements.
To validate and test our proposed method, we applied it to two popular mathematics datasets, GSM-8K, which consists of grade school math problems, and Math, which includes high school math competition problems. We evaluated the performance improvements by comparing our method against two baselines, zero-shot COT and rejective sampling fine-tuning, RFT. The metrics used to assess performance were accuracy rates, which were reported in our experimental results. We observed that our methods consistently outperformed the baselines, with accuracies improving during iterative training, although performance converged quickly. Additionally, we conducted transferability evaluations by training on one dataset and testing on the other, confirming that our methods enhanced the mathematical reasoning ability of the models, as indicated by better performance on unseen datasets.
What specific results did your method achieve? And how do these results compare with baseline methods in terms of accuracy and improvements over iterations?
Our proposed method consistently outperformed baseline methods, achieving significant accuracy improvements during iterative training on the GSM-8K and Math datasets. Specifically, we noted that the performance converged quickly, with only about 2,000 problems from each dataset being utilized for training, indicating efficient learning. The results showed that our method surpassed zero-shot COT and step-level DPO, with the latter yielding only marginal improvements on Math, underscoring the superiority of our data generation approach. Additionally, while the accuracy improved over iterations, it was observed that the performance on GSM-8K converged more rapidly than on Math, likely due to the lower difficulty of GSM-8K problems. Overall, our method demonstrated a robust enhancement in mathematical reasoning ability, as evidenced by better performance on unseen datasets compared to the baselines.